In this video, I will go over a couple of key definitions relating to machine learning algorithms, which is important to understand. This is in continuation of the previous two videos of Introduction to Machine Learning, where I have gone through machine learning from a sort of practical engineering perspective. But I want to extend those videos with a couple of definitions, which is useful to make clear. So, to recap, the definition of machine learning is an algorithm that can learn from data. And learning, as we discussed, means acquiring knowledge. And that's what machine learning methods are doing. They recover or learn knowledge from a set of data and encodes this knowledge as a model of the underlying system. And as we discussed, there is of course nothing magic to this process. The information we have to retrieve must be in the data to begin with. Otherwise, machine learning doesn't work. We really need this engineering perspective here of actually understanding what we are trying to do and making sure that the information or knowledge we are looking for exists in the data. And that is true for all machine learning methods. A slightly more scientific definition of machine learning, which was published in 1997 already by Tom Mitchell, and it's still quoted today, is the following: that a computer program is said to learn from experience E with respect to some class of tasks T and performance measure P if its performance at tasks in T as measured by P improves with experience E. Now, this is a bit more sort of engineering technical definition than what we discussed in the previous videos, and I think it's useful to understand what Mitchell means with this. So let's try to break this definition down a bit. So the first paragraph here talks about tasks T, which can really be anything a computer can do, like playing a game, performing pattern recognition, even controlling a system, controlling some physical system. All of this is tasks that computers routinely do. And the experience is simply any data, measurements, images, and so on that we would like the computer program to utilize in the machine learning setting. And the performance P is simply the quantified success in performing task T. So how well are the algorithm doing? How good are we at performing task T? And machine learning is then utilizing the experience E, the knowledge that we can extract from the experience E, the data, the measurements, in order to build models that allows us to improve our performance at some task. So that's another way of looking at machine learning, which is essentially what we discussed in the previous videos, but it's a slightly more technical definition of this concept, machine learning. Another definition which is useful to be familiar with and which comes up in discussions around machine learning quite often is the distinction between artificial intelligence, or AI, and machine learning. And for people who are not really experienced in the field, these terms are quite often and somewhat unfortunately used interchangeably, even though they are definitely not. And therefore it's nice to just give a quick overview of how these terms relate to each other. And this figure is borrowed from the deeplearningbook.org, which I can highly recommend for those of you who are interested in a more in-depth discussion on machine learning. And according to this figure, the field of AI is kind of the broader field. So any algorithm or software which attempts to mimic intelligence in some way can be said to be artificially intelligent. So it's a whole bunch of methods, like search methods, knowledge bases method, as they mention here. But a subset of this act of mimicking biological intelligence is the act of learning, or machine learning methods. So from this definition, it's clear that machine learning is a subset of AI. There are AI methods which are not learning by Mitchell's definition, and therefore are not machine learning methods, but they are still AI. But all machine learning methods can also be said to be AI methods. And just to follow these definitions a little bit further, for those of you who are interested in deep learning, this is again a subset of machine learning. This is also two terms that are in uninitiated circles used interchangeably sometimes, which is again unfortunate because they are really not. There are many machine learning approaches which really aren't deep learning, such as logistic regression, decision trees, and so on. But deep learning is again then a subset of machine learning. This is something which we will return to in a later video. What methods could we then consider machine learning based on these definitions? Well, artificial neural networks, definitely, evolutionary algorithms, decision trees, regression models, and much more. All of these are machine learning tools, something which learns from experience. It is useful to divide up all of these methods for machine learning, and there really are a lot, into some subcategories just to get a more overview of the field. And a common way of doing that is these three categories, which is named supervised, unsupervised, and reinforcement learning. I'll just give an overview very quickly first of what these three are, and then go through them in a little more detail in the next few slides. So first, unsupervised learning is methods that is looking for patterns in the data. That's where we have a single data set and no references. I'll explain in the next slides what that means. And the output of an unsupervised learning method is some kind of model that can somehow describe the structure of the data. How can we segment the data in some way in order to fulfill some optimization criteria? One way could be to try and find sets within the data that are similar in some way. So we segment the data in subsets that are somehow similar. For example, using something like Shannon entropy to minimize Shannon entropy for the data sets. Another way, or another type of machine learning methods, is what we call supervised learning. And now we have two sets or two parts of data, one which we call the input X and one which we call the output Y. And the goal here is to somehow learn the knowledge or build a knowledge model that can describe this mapping from X to Y. So how do we get to the output Y from the input X? So then we need sets of pre-classified data, data where we know what the answer is, and we try to learn how to compute that answer from sets of data that already has the answer. And then we can apply that in the new data sets where we only have the inputs X and we try to predict the outputs Y. This is probably the most typical approach in engineering, where we very often have systems where we would like to learn what happens if inputs are such and such, what happens to the system, what can we generate out of the system. This is probably the most common scenario in engineering. And the third type of machine learning methods is something we call reinforcement learning. And unlike the first two, unsupervised and supervised, which both learn from historical data, so sort of batch mode learning, where we have historical data sets that we go through. In the reinforcement learning scenario, we have a form of learning which we might call online, meaning that we have a system or an agent, as it's called in reinforcement learning, that learns from its actions. So it's a system that performs actions and then tries to learn a model which describes or represents knowledge of how the agent's actions or has consequences for its environment. So which actions are beneficial and which actions are detrimental with respect to some defined goal given different environment states. A little bit more detailed discussions of each of these three. Supervised learning first. As I mentioned in the previous slide, the supervised learning paradigm, we deal with an input and output dataset. An example of such a dataset could be, for example, images of fruit. Here, unfortunately, all the apples are the same and the oranges are the same, which would be quite bad for machine learning. But as an example, I guess it's sufficient to explain the point. So what we have here is 6 images, where each of the images have been pre-labeled by a human, denominating what is an apple and what is an orange. And the goal of the algorithm is then to look at the individual images and try to learn a model which allows it to correctly apply the label apple or orange to each individual image. And the model then represents this knowledge of how to perform such a mapping. Formally, this mapping is very often defined as a mathematical function, like let's say y equal to g of x. Remember where that x is the input and y is the output. You can think of it something like this, that we then have a new fruit where there is no label, which is then, if it's an apple, it will be assigned the label apple, and then if it's an orange, it gets the label orange. So from this data, we learn a model, and then this model can be used to apply labels to new images. That's the this mapping of supervised learning. There are 2 forms of supervised learning, one which we call regression and one which we call classification. And in the regression setting, we are typically, then we calculate the number, so it's some kind of scalar or vectorized output, which we are computing. So typically linear regression or PLSR would be another example of such methods. Neural networks also. Whereas the labeling algorithms are known as classification algorithms. Then we don't compute a number, or we are at least not interested in the number itself, but the goal is to apply one of a discrete defined set of labels to the input data. There are, of course, many methods that are classified as supervised learning, such as neural networks, decision trees, and so on. And many of these can be used both for regression and classification, depending on how you define your problem and how you configure the different methods. In the unsupervised learning case, I have used the exact same set of fruits, but I have removed the labels just to sort of illustrate the point that the key difference between supervised and unsupervised learning is that for the unsupervised paradigm, we don't have any pre-classifications. We just have a set of data, and we have no information other than our inputs. So it can be a set of unlabeled images, or it can more typically be some set of data points that we would like to construct a model of. And the model that we wish to learn in unsupervised learning is some kind of representation of similarities of different inputs, so that we can group them together in some way. The goal is to obtain subsets of the data which are homogeneous to some degree, or in some defined optimal sense. So we can then train a model, and we might obtain something like this, where the algorithm would find that this region of the image space would contain fruits that are sort of similar. In this case, they are identical, but they are apples. But the algorithm wouldn't have any notion that this is apples. It would just try to look for objects that are similar and say, okay, these 3 are similar and these 3 are different than these 3. And therefore, we might segment the data as is described by this hand-drawn black line here. Typical examples of unsupervised learning would be nearest neighbor, k-means clustering, and yeah, lots of other methods. PCA, principal component analysis, is often considered unsupervised learning. Well, it is unsupervised learning. The third type of machine learning method, which it's important to be aware of, is this reinforcement learning. And as we discussed, this is an online learning paradigm, where rather than having a bunch of historical data in a data set, we learn from observations of the environment state. So we have a loop, which is something like this, where the program, or the agent as it's called here, performs an action on its environment, and then from that action results a new environment state and also a computed reward function. So the agent gets a reward, can be positive or negative, which then results in the agent being able to build up a knowledge model of how its actions influence the environment. So what is a good action and what is a bad action for a given environment state. So an example of a reinforcement learning scenario would be a robot that tries to learn how to sort fruit, so sort different fruits separately. The setup would be something like we perform an action, which would be to move a fruit somewhere, and then we observe the fruits or the environment state. Then we try to estimate the reward function, which would then be, for example, trying to compute the entropy of the set of fruits, if they are ordered or disordered. And then finally we would then evaluate the action we performed based on the reward we get from doing that action. So if the changes to the environment is favorable or not. And after many repeated such actions, we will then have a model which contains the knowledge of how to sort fruit. So it might very simplistically look something like this, where you have this disorganized set of fruit. Maybe the first action would be to move an apple over here, which we see doesn't really affect the ordering of the fruit. It's still pretty much mixed together. So the reward here would be pretty low. The action didn't really provide any favorable outcomes. But after many iterations, we would eventually get something like this, where the agent is now move the fruit around until the environment becomes favorable as per our definition of being organized. And after further iterations, maybe we end up with something like this, where the agent has now learned properly how to shift fruit around in order to achieve an ordered set of fruits. And the learning happens here as these actions are performed, and as the actions produce a change in the environment state, we get our reward, evaluate the action, and then we get better and better at sorting fruit or whatever else action we might wish to reinforcement learn. So in quick summary, as we have seen in previous videos as well, machine learning is really the act of extracting knowledge from data, or in the case of reinforcement learning, it's online observations, which is sort of still data, and encode that knowledge into some model, which then allows us to improve the performance that we achieve on some defined task. And there are many different types of methods. We discussed now unsupervised, supervised, and reinforcement learning as a way to classify these different approaches. And which of these methods or types of methods one would apply, it's entirely depending on the application or the goal of our project, what we are actually trying to achieve. And that's what determines which type of method we wish to use.